Hello, I'm Hannah Sachs, Editor-in-Chief of NEJM Evidence, and this is Stat. Summer camp. Canoeing on the lake, telling ghost stories around the fire, and hanging out with friends. What could be better? Bzzz. Splat! Those pesky mosquitoes really ruin the vibe. Imagine you're a dedicated camp counselor and budding clinical trialist trying to optimize the summer camp experience. So you plan to test a new insect repellent, Buzz Off, and compare it against the existing spray, No-Skeeto. You plan to give some campers Buzz Off, other campers No-Skeeto, and see who gets more mosquito bites. But as you think about it more, you realize it might be challenging to randomize individual campers to either Buzz Off or No-Skeeto. The sprays are aerosolized, so one camper in the Buzz Off group might be caught in the crossfire of their bunkmate's No-Skeeto spray. It also seems likely that a bleary-eyed camper might accidentally grab their neighbor's repellent in the morning and use the wrong one. This problem, called contamination, occurs when one group in a trial is unintentionally exposed to the other group's intervention. Contamination dilutes the perceived effect of the intervention and makes it harder to detect a difference, if there really is one. In other words, it increases the probability of a type 2 error, or false negative. So what's an aspiring camp trialist to do? Well, one approach is a cluster randomized controlled trial. In cluster RCTs, you randomize entire groups of individuals, or clusters, instead of individual participants. Clusters can range in size from small groups like a household to larger groups like hospital floors or clinics, or even entire cities. You decide that for your trial, the cluster will be a cabin of campers. Once everyone in each cabin has been sprayed with either Buzz Off or No-Skeeto, they can go interact with their fellow campers from other cabins with a pretty low risk of contamination. There are other situations that would prompt consideration of cluster RCTs. First, cluster RCTs are particularly useful when studying large-scale intervention, such as health system-wide changes or public health interventions. If you're trying to study the effect of a new alert in the electronic health record, for example, the unit of randomization could become the entire hospital or clinic that would be affected by that change. Second, cluster RCTs are often the best trial design from a logistical perspective. Let's say you want to test whether a later school start time improves sleep duration for teenagers. It might be a logistical nightmare to randomize some students to start at 7:30 a.m. and others at the same school to start at 9:30 a.m. A more efficient experimental design would be to randomize some schools to start early and some schools to start later, with each school being a cluster. But cluster RCTs tend to be more complex to design and analyze than individual RCTs. By design, clusters include individuals that share similar characteristics, and consequently, their outcomes are not statistically independent. In your trial, for example, the individuals within the same cabin may be more likely to have similar numbers of mosquito bites to each other than to individuals in another cabin, because of different factors, like their proximity to the lake where mosquitoes breed. In cluster RCTs, one parameter that's important to consider is what's called the intra-cluster correlation coefficient, a measure of the extent to which individuals within the same cluster are more similar to each other than to individuals from other clusters. Mathematically, the ICC is the ratio of between-cluster variance to total variance, which includes both between-cluster and within-cluster variance. ICC values range between 0 and 1, with values closer to 0 representing large within-cluster variation and values of 1 representing no within-cluster variation. With no within-cluster variation, one participant from the cluster provides as much information as all of the participants from the cluster. One of the benefits of individual RCTs is that randomization typically balances baseline confounders, whether measured or unmeasured. However, with cluster RCTs, there can be baseline confounders between clusters that are harder to balance through randomization. For example, as we discussed, cabin proximity to the lake may be an important factor. To account for this, you could stratify randomization by proximity to the lake to make sure that an equal number of clusters close to and far from the lake end up in the Buzz Off and No-Skeeto groups. There are additional complexities in the design and analysis of cluster RCTs. For example, whether to analyze the outcomes at the individual or the cluster level. But the point for now is that it's important to take clustering into account at both the design and analysis phase of a trial. All these complexities bugging you? Make sure to consult with a statistician before designing your cluster RCT.